need to stop the video while I'm sharing. Hold on.
All right, Karen, I went ahead and turned off your video, so.
Right, good. Okay. All right, I'm going to have to stop sharing and restart. Okay. Hopefully that helps. Mass timber refers to a group of products, including what you see here. I was saying that typically we use post and beam, which is shown on the left, made up of glulams, and then the floor or roof plate is either CLT, cross-laminated timber, made of solid sawn laminations, the top middle, or made up of CL laminations like a plywood basically, but really fat and thick, shown on the top right. But mass timber also can be dowel laminated timber, DLT, nail laminated timber, NLT, or glue laminated timber, GLT. Each of these is just 2x wood laminated together with either hardwood dowels or nails or screws or adhesive. And then solid sawn is what we're going to be focusing on today, solid sawn CLT, as that's what's being used most and what's being tested for protective design. So it's made up of either 3 or more layers of 2x material that are oriented in or alternating directions and glued with a structural adhesive. And the panels can be up to 12 foot wide and 64 feet long, with thicknesses ranging from 3 to 9 ply. These are some of the most common layups that you'll find from the manufacturers, although custom layups can be made as well. Usually it's an odd number of plies, so there is a strong and a weak direction with the span, but there is two-way capacity to span 2 ways. And the price is proportional to the wood fiber, so you're going to find your best, most efficient planks in either 3 or 5 layers. And CLT has been in the code since 2015 IBC. Back then it referenced the NDS and the APA PRG 320 product standard. And then looking ahead to the 2021 IBC, this has got 3 new building types, which are really exciting. It's 4A, 4B, and 4C. What used to be called Type 4 in 2018 IBC and earlier is now called 4HT for heavy timber. And the 4HT still uses the prescriptive sizes that were described in the previous codes. But these 3 new building types allow you to have up to 18 stories and 270 feet of wood construction, which is awesome. And it's primarily done in mass timber. And then the PRG 320 is the APA standard for CLT that covers things like dimension tolerances, structural performance requirements, and quality assurance. That's a free download from the APA, American Plywood Association. And then in addition, each CLT manufacturer has their own qualification reports that's specific to their product. This is one area where CLT is a little bit different than like specifying steel from the steel manual. And that every CLT manufacturer has different species of wood. They have different grades and layups and capabilities on width and length of panel with their equipment. So every manufacturer is going to have different strengths, different stiffnesses, similar to doing like a pre-engineered metal building if you've designed those before. The best way to do this, or the most efficient maybe way to do this, is to engage the manufacturer during the design phase. And that way you can tailor your design to their strength values, their manufacturing capabilities, and usually they've got an engineer on board or engineers on board that can help make the project efficient, help design the panels and the connections, and that kind of thing. But since we're talking government projects today, hiring the manufacturer early may not be possible, but and if that's the case, you can go design, bid, build, the more traditional route. But then the design just needs to be a little more generic and may require some tweaking after the project is awarded. So you can find a detailed list of manufacturers on our website, or you can contact us, and we're happy to provide you some more information on that. And that sums up just mass timber systems and general overview of what they are and how they work. And we're going to move into fire resistance. This is definitely a topic of interest in anybody when you're talking about 18 stories of wood. It's the first question that comes up. They want to know how it's going to perform in the event of a fire. So the main thing to understand is that mass timber and heavy timber don't burn the same way light frame does. Think of like, a great big log in your fire pit. It's just not going to burn the same way because there's a lot of mass and less surface area. The wood burns at a slow, even rate that we can predict very accurately. And as it burns, it forms this kind of char layer on the outside that helps protect the wood on the inside. And the inside wood retains its structural properties because of this char layer on the outside. So this has been well known for many years. It's well documented in the NDS. So the way you determine a 1 hour fire rating is not through tested assemblies, but through a calculation. You calculate how much wood is left after a 1 hour fire, for example, and you would determine the structural capacity for the remaining wood using temporary conditions. So you get a little bit of a bump up in the stress because you're just doing kind of temporary load conditions. So it's a really simple calculation. It's detailed in Chapter 16 of the NDS. And here is the code path for that. IBC 722.1 says to calculate the fire resistance rating of exposed wood members using Chapter 16. And then AWC has also put out this technical report called TR10, which has design examples and kind of walks you through how to use Chapter 16 if you're not familiar. And since fire is often an architectural design or architectural consideration, and the NDS calculation is something that the structural engineer would do, it's someplace where they need to collaborate here, which isn't something that is typical of steel and concrete buildings. And just a note that designers tend to think that steel isn't a problem in fire since it's not combustible, but it just responds differently. It loses strength and yields in higher temperatures. You can see in this picture to the right, this is a steel beam and a glulam beam that were in the same fire. You can see that the steel has yielded and the glulam has charred. And the chart on the left here is showing time on the x-axis and percent strength on the y. And what it's showing is that after 30 minutes exposed to the fire, the structural steel has lost 90% of its structural properties. And after that same 30 minutes, the wood has lost about 25%. So you do have to make sure you've got enough mass to take care of that when you're designing for a fire event, but it really performs quite well. Okay, that's my super quick fire resistance talk. So these are going pretty fast. So again, if you want to know more, we can provide more information. So next, we're going to move on to acoustics. Let's see. Okay. So the IBC doesn't give much in the way of guidelines or recommendations for acoustics. The only thing they do say is that for residential occupancies, the walls and the floors that separate one unit from the next or one unit from a common area need to have an STC rating of 50. And they also require an IIC rating of 50 in the floor and ceiling assemblies. But there's no other recommendations for other occupancies but generally speaking, 50 is a good number to shoot for when looking at acoustics. And this is a chart that shows the STC and IIC of just bare CLT panels. So you can see here a 5-ply, which is 6 7/8 inches thick, is going to get us to an STC of 41 and an IIC of 25. So just bare CLT panels are not going to be enough to perform well acoustically. Therefore, this is a common floor assembly that designers like to use. It performs well. It allows the wood to be exposed on the underside, which is what most designers and owners, developers want. And then directly on top of the panel is an acoustical mat, and then 1 to 3 inches of gypcrete or concrete, and then your finished floor. This assembly not only helps with acoustics, but will also help with vibration, which often controls with mass timber. And we have great resources on this on our website. This is just a screenshot of our acoustically tested mass timber assembly index, and that just gives a bunch of different assemblies with a bunch of different manufacturers and gives you the STC and IIC ratings. All right, so let's talk about why people are being driven to use mass timber in their projects. Well, as of June 2023, we've got 1,860 multifamily, commercial, or institutional projects that are in design or have been constructed with mass timber across the U.S. This graphic is showing those projects where construction has been completed, which is exhibiting exponential growth. And the reason for this, well, some of the reasons for this, are the primary drivers that we've found. The biggest one is construction efficiency and speed. Because all of these are pre-engineered, they're pre-manufactured, fit together precisely. It's kind of like a kit of parts. The structure goes up really fast. So if you've got something like a school that needs to be done over the summer, mass timber really lends itself well to that kind of thing. Additionally, if you've got a tight site, mass timber works really well for that because often the crane is just picking the pieces right off the truck as it comes in and putting them right in place. There's not a lot of storage needed. And obviously it's innovative, it's new, it's got a great aesthetic, people love it. And then it's got a sustainability story that, and we'll talk a little bit about sustainability here in a minute, but it's definitely a perk and a driver for most folks. And then it's got great structural performance in relation to its weight. It's a very lightweight structure. And this is just to get a little taste of what I mean by that. This is Brock Commons. It's 18-story mass timber student residence hall in Vancouver, British Columbia. This project exhibits several benefits. The slide is showing the fast construction speed and the fewer number of skilled laborers that were needed here. A more traditional building, steel or concrete, would have had about 100 people on the site at any given time and a 7 to 10 day floor cycle, plus shoring and curing time. But they found when using mass timber, they had more like 20 to 30 people on site and 3 days per floor with no shoring, no curing time. Additionally, the MEP came up right behind the structure, so they were able to work because there weren't any, shores in the way and that kind of thing. They could just follow right on ahead. And then the environmental benefits are a big factor. Wood does take energy and carbon to harvest and produce, but when compared to more traditional methods, it has a huge reduction in greenhouse gas. So this is a really big topic with a lot of research ongoing. We've got a couple of experts on our staff in the sustainability space if you're interested in more information. But this is just a carbon calculator result, which is a free tool on our website that you can use that gives approximations on the greenhouse gas emissions that were saved by using wood. And the fact that it's lightweight is also a big perk. If you have a project that has poor soils, for example, this is a really good option. If you have something that's got limited capacity, like you're adding a story or two onto an existing building foundation, that's been really popular. We have several projects now where they've used mass timber to build on top, and if the structure was designed for 2 additional stories, they were able to get 3 or more using mass timber. And it results in savings by utilizing smaller cranes and construction equipment as well. And then the structure being the finish saves a lot of time and money because you're not installing all that gyp, all those hung ceilings, and looks much better, at least in my opinion. And if you've done any research into biophilia, you know that being in an environment with natural materials can have health benefits and lower stress. Very appealing to most people. All right, so what about cost? There's another big topic, right? Well, the main thing to know when comparing steel or concrete to mass timber is that you need to look at the whole project. Mass timber is kind of a different animal in several ways. You can see here that 64% of the cost in a mass timber building is in materials, and labor is only 14%. So with another construction material, that's kind of flipped. It's more labor, less materials. So what happens is, an architect or an engineer might decide to compare costs, and they might look at a typical steel bay and a typical mass timber bay for cost and find that the mass timber is more expensive, and then that's usually where it gets the boot. But there's a lot more to consider, a lot more that should be considered. This is a list of several factors that result in savings on a mass timber project. Things like cure time, there is none. Crane size, all your foundations are typically smaller. You've got fewer finishes, a lot less gyp. Your construction speed, that's a huge one. Labor costs, and then you get occupancy about 25% sooner, which has a big impact, especially if the building is going to be turned over to somebody else or it needs occupancy quickly. And then the exposed wood tends to achieve greater leasing velocity than standard steel or concrete. So we've got several business case studies on our website that include the finances of built projects as reported by the developers. The idea is that a developer or investor can take a look at these case studies, which talk about the qualitative influences, the quantitative data, examine the investment successes and challenges and lessons learned to make a decision for themselves. So Dohe Hall is one example. It's a residential and classroom building for the University of Arkansas. The construction cost on this one was compared to an equivalent project built of steel and concrete, and they found that the mass timber came at about a 4% premium. But then when the developer determined the benefits, such as the faster build and the beautiful end product, decided that that far outweighed the premium, and they went ahead with the mass timber. Another pricing example is the Canyons project. This is a smaller project. It's a 5/1 structure designed with mass timber floors, but then went through a value engineering exercise to look at light frame wood as an alternative. So they determined using I-joists and drywall would save about $278,000, and weighed that against the value lost, such as the construction, the ceiling height, the aesthetic, and the valuation of the building when sold, and they decided to keep it in mass timber. And then if you were looking at a larger scale building, usually the cost either just about equivalent or a few percentage points above indirect costs, but then with lower overhead costs, such as general conditions. And it ends up being a wash for most projects. Sometimes you get 2 or 3 or 4% higher for the mass timber, but then you get the move-in date that might be 20 to 25% sooner. So, ultimately, the lesson learned is if you're comparing costs, just look at the project holistically. All right, covered a lot very quickly here. We're going to move on to sustainability. And I think we're doing okay on time. I've got about 15 minutes. Okay, first I want to just quickly touch on forestry, as there's a lot of misconceptions out there about cutting down trees. The chart here is showing forested acreage in the U.S. from our earliest estimates before the major development of European colonists to today. You can see there was a big dip in the 1800s, but since then, forest land has been stable since the 1900s. And keep in mind, during this time, our population has gone, from 76 million to about 330 million. So we've had a big increase in population, but everything else has stayed stable and actually increased ever so slightly. Canada is very similar. They've got about 91% of their original forest cover, which is more than any other country in the world. We have trees. We're good in the tree department. And if you want to not just look at acreage, but in volume, tree volume has actually increased in the last 60 plus years. The colors here represent the north, south, and west regions of the U.S. And this considers all losses, including natural death of trees, wildfire, harvesting, insects. So this really does exhibit the sustainability of United States trees. And note that this does not include national parks and wilderness areas, because those are considered preserves and not timberlands. So this is only the timberland area. And then this map is showing current distribution of forest land throughout the U.S. Dark green is publicly owned and light green is privately owned. So what's interesting here is that 56% is privately owned. And of that 56, 42 of that 56 is owned by individuals and families, where corporations, partnerships, and tribes own the other 14%. So why would that matter? Main thing is when you think about what motivates families and individuals to keep forest on their lands is the economic value of the forest products, primarily at least. It might not be the only consideration. So the more economic incentive we can give to create sustainable forestry, the better. The simple truth is that forest survival often depends, in most cases, on its value to the community and to the people that own it. So if we decide that wood and paper products, using wood and paper products, helps keep sustainable forests and trees, then how can it also help the environment? When we look at global carbon dioxide emissions across various sectors, we find that the building industry accounts for about 36% of emissions, which is huge. If you break that down further, 27% is operational carbon and 9% is embodied. So what does that mean? Operational carbon in blue is referring to like the heating, the cooling, and the powering of the building while it's in use. HVAC system, all of that stuff. Electricity, whereas embodied carbon, the orange there, is the energy used to build the building. And that includes the harvesting and the fabrication of materials, the transportation to get the materials there, powering of all the equipment, and so on. So most studies that those that are familiar with, LCAs and carbon and all of that stuff in the built environment, most studies are looking at the operational carbon. They want have more efficient HVAC units, and they want better insulation and all of that, which is, great, important. But embodied is substantial. It's a substantial piece and shouldn't be ignored. So just building our new buildings accounts for 9% of global carbon dioxide emissions. You can see that removing or reducing the embodied carbon dioxide during the building process can have a significant effect. All right, this chart is a little tricky. The x-axis here is the time from when a building opens its doors, and the y-axis is the percent of energy that creates emissions. So on day one, which here is shown 2020, on day one, 100% of the energy of a building is embodied. That's the energy that it took to build. And then it opens its doors, and then the operational starts, right? Operational energy to heat and cool and power the building. So as the operational energy goes up, the embodied goes down because we're looking at percentages here. So it takes about 17 years is what this chart is trying to show before we get to 50-50, where the operational has become equal to the embodied carbon that was made to build the building. What we're getting at here is it's significant, 17 years. And even after, 50 years, the embodied energy is still 25% of the building's overall energy use. So we've covered that embodied carbon is significant. So how does using wood help with that? Well, if you look at the kind of dark circle here, I don't know if that's brown or black, but that's the natural cycle of trees. They grow in forests. They remove carbon from the atmosphere as they grow. They get larger, and then they eventually die, whether or not that's natural causes or fire or insects. And once they die, then they start releasing that carbon back into the atmosphere, and that's the natural cycle. And so if we are taking the trees down before they meet the end of their life, and we're using them for buildings or for furniture or what have you, then we're storing that carbon, and trees are 50% carbon by dry weight. So we're storing all that carbon in those buildings, in that furniture, until a time when they are to the end of their useful life, in which case, assuming they're not recycled, then they release the carbon at that point. So it is kind of a circular loop, which is a little bit different than other building materials. So it is a material that requires a minimal amount of energy-based processing. It has a low level of embodied carbon relative to other materials used in construction. And since the sun provides the energy to grow the trees from which we produce wood products, whereas fossil fuels are the primary energy source in steel and concrete manufacture, it really is a lot more efficient as far as sustainability goes. And these conclusions can be tracked and quantified by life cycle assessment analysis. We've got several studies now on our website that include a whole building life cycle assessment and a life cycle costing, where we've compared a mass timber building to an equivalent building of steel and concrete. This one here is Plat 15, and it was done by KL&A engineers. And it was done on this commercial office building in Denver to understand the cost and the global warming implications of different structural materials. So the building is an actual building that was built in Denver, and it was done in mass timber. And then the engineering firm that designed it went back and redesigned it in steel, and then redesigned it again in concrete. And then an LCA was done on each. And this chart is really super oversimplification, so please go read the full report if you're interested in it. But since we're going fast here today, the mass timber building is shown in green, and that's going to be our baseline. So that's going to be at 100% of our global warming potential. That's GWP. So when we look at 100% for green, which is mass timber, and we compare that to the steel in blue, steel is about 325%. So over 3 times the global warming potential with the steel building. And then the concrete is over 4 times as much. So big difference in the global warming potential on each of these. And then when you look at the cost of all 3 buildings is very similar, with just a few percentage points different. Full disclosure, I think when you read the report, you'll see the actual numbers, but I think the mass timber building was like 3% higher or something in cost. But they were all really close in there, and the global warming potential was not. So it was a very interesting study. We have a number of resources on our website on sustainability in the form of these expert tips. I'm just going to kind of show them here real briefly so you can get a feel for what's on there. They're listed on our sustainability landing page, which you can either use the QR code here or just go to our website, woodworks.org, and search sustainability. Okay, last topic, blast ballistics, forced entry testing and design. Right, this is a high-level overview of some of the research that's been performed to date in this space for protective design. Woodworks was involved in multiple blast tests of CLT panels in 2017. Then there was ballistics and forced entry tests have been performed since then. There is currently no code or accepted standards for designing mass timber for progressive collapse. However, those are underway. And we've got this Woodworks paper I'll show you here briefly that is kind of the start to the progressive collapse story. And then in addition, K&C, which is a blast consultant, is working with the Army Corps of Engineers to update the UFC progressive collapse document to include mass timber. So that's ongoing. And then the blast testing was designed to investigate the performance of CLT for Department of Defense anti-terrorism blast loads. This was done pre-2018, so it used the more stringent requirements that were in place at the time. They include the quasi-static tests with and without axial load, and then the arena blast tests were done at Tyndall on full-scale structures. We've got lots of information on these, as well as the full reports on our website. And then this is just a screenshot of our protective design page on our website that's got a lot of information and links to the PDC requirements and the test results. So if you really want to dig into this, you can check it out here. And then this is a quick video that's going to show one of the arena tests, which is super fun. So I'm going to kind of describe it here before I start it. You're going to be able to see the shock wave coming from right to left across your screen. And then you'll see the response of the CLT panels, and then the rebound, followed by the rupture of the outside of the panels. Most of the damage is in the rebound. And these are all 3-ply CLT panels, and the blast has been designed to push them to rupture. So overall, they performed very well. So let me see if I can get this started. Okay, blast, shock wave, and response, and rebound, and rupture. I don't know if there's any lag in my video or anything, if that made any sense to you at all, but I thought it was pretty cool. So the main takeaways were that mass timber structures can be designed to resist blast loading. They actually perform rather well. And that the rebound response must be considered for both the panel and the connection design.
Question, by rebound, do you mean the negative pressure wave?
Yeah, yeah.